So important velocity fact number 2, when velocity is positive, motion is forward. So probably you've guessed when velocity is negative, then motion is backward. So the key fact, something that you're going to have to know for the AP test, this comes up frequently, direction changes. So direction meaning whether you're going forward or backward. So the change between going forward and going backward, that occurs when velocity changes sign. So the last answer here is changes sign. And just to clarify, changes sign means either changes from positive to negative or from negative to positive. Now the only time a function, a continuous function at least, can change from negative to positive is if it changes through 0. But that's different from saying that direction changes when velocity is 0. Direction changes when velocity changes sign. So here's an example. Is a velocity graph. That's a graph of v of t is shown here. At what time or times does the particle change direction? Well, the particle changes direction at time t equals 3 because the velocity changed from negative to positive. Notice that here, what color? I'll use red. Before time equals 3, the velocity was negative, meaning velocity was below the time axis. And right at time 3, the velocity all of a sudden has become positive. It becomes above the x-axis. So, and then there's a second place, and that's when time equals 5. If you were asked to give a reason for your answer, you would say because velocity changes from positive to negative at time equals 5. Before time 5, the velocity was above the t-axis, so the velocity was positive, and then after time 5, the velocity is below. So at time t equals 5, velocity changes from positive to negative. Acceleration is the rate at which velocity changes. So acceleration is the derivative of velocity, which means that acceleration must be the second derivative of position. So you can see the notes to fill in on your paper here. Acceleration is the derivative of velocity. So a of t, the acceleration function, as the acceleration as a function of time t is equal to v prime of t, which is equal to s double prime of t, if s is the position function. So here's another problem. The position of a particle that's moving in a straight line is given by s of t is t squared plus 4t plus 4. Find the acceleration of the particle at time t. Well, to find the acceleration at time t equals 4, what I'm looking for is a of 4. But before I can figure out a of 4, I have to find a of t. A of t I'm going to find by taking the first derivative and then the second derivative of position. Then I'm going to be able to plug in 4. So here's my work down here. I have position, that's the s function. I'll start by finding velocity, which is the derivative of position. So I think you guys are experts at finding derivatives of polynomials now. Here's my velocity function. To find acceleration, I'm going to take the derivative of velocity. So I get 2. So a of t is 2. This is interesting. It means that a of t is a constant. That means no matter what time t I use, the acceleration is always the same. The acceleration is 2. So to answer their question, the acceleration at time 4 is 2. This is just a graph so we can practice thinking about the relationship between distance and velocity and acceleration. So we know velocity is the derivative of position, and we know derivative means slope. So velocity is the slope of the position function, which means anytime the slope of the position function is positive, anytime the position function goes uphill, then velocity must be positive. So here I can see that this position function goes uphill all the way to sort of that middle time value. And notice that we can say velocity is positive for all those places. The position function goes downhill, so must have a negative slope, whatever after this time t equals, I don't know, t1. So here, if the position function goes downhill, velocity must be negative. So we have, you can see here I've said velocity is negative for all these sections. And then what do we know about acceleration? Acceleration is the derivative of velocity, which means it's going to be the slope of the position function. So let me get a new board here. So take a look at this first piece of the function. We see position is going uphill, so that's why we knew velocity was positive. And think about the slope. Think about the slope of this little piece of the function. It's not a line. This isn't a graph of a line, so the slope isn't always the same. What's happening to the slope? Is the slope getting bigger? Is it getting steeper? We know the slope is positive. Is the slope getting steeper, so the slope is increasing? Or is the slope flattening out? The slope would be then decreasing. So here I think this is getting steeper and steeper. That means the velocity is increasing, which means the acceleration must be positive. Here for this piece, if you just kind of draw over it, it kind of looks like a line. So the slope is about the same. The slope is positive, but the slope stays about the same. So the velocity is constant, which means the acceleration is 0, because the derivative of constant is 0. So you can sort of walk through the rest of that picture just to kind of get a hang of the relationship again between position, velocity, and acceleration. And then just one more idea here for this video. We've talked about average rate of change in y over change in x. And if we take the limit as those 2 points on our graph get closer and closer together, what we have is instantaneous rate of change, which we've been calling derivative. So derivative is the slope of a function. It's also the instantaneous rate of change. So the rate at which something is changing right now. So instantaneous velocity, it's the rate right now at which the distance is changing. But this works for no matter whatever kind of function you want to use. It doesn't have to be a position function, a velocity function. We can talk about the rate of change of functions that represent any kind of quantities. So check out this example. So we know that the area of a circle is equal to pi r squared. So the area of a circle is dependent on, it depends on the radius. So we could take the derivative of this function. Let me get a pencil. We could take the derivative of the area with respect to the one variable that it depends on, which is the radius. So pi is a constant multiplier, so pi kind of comes out to the front. The derivative of r squared, the 2 comes to the front, and the new exponent on r is going to be 1. So the derivative of area with respect to radius, so dA dr, is going to be the derivative of pi r squared, which is 2 pi r. And then there's one more question on your paper, and that says, what is the rate of change of the area of the tree trunk, for example, at the exact moment when the radius is 4 feet? So the notation we use here, dA dr, so the rate of change of the area with respect to the radius, at the exact moment when r equals 4, so we say dA dr, we use this tall vertical line, and then right at the bottom we're going to write r equals 4. So what that means is we're going to take the formula we got, 2 pi r, and plug in 4 for r. So dA dr when r equals 4 is 2 times pi times 4, which equals 8 pi.